let's go for the other part, which is what I called attentional oscillations. And by attentional oscillation, I'm talking about how these parts of the brain that we discussed about before, frontal, parietal, occipital, these pieces, are talking to each other via connections. As I told you before, in this kind of rat model brain, these connections are going to be important. It's not just about activations that we saw in the previous parts in terms of, okay, these are the activated activations. It is not just about activation. It's also about how these parts are connected and where is, or what is the process of information flow from the front to back or back to front, and how these parts are integrated to each other. People realize that these kind of connections could be related to oscillation as well. So oscillation is going to be important. So two areas that are connected would start to oscillate together. So oscillation would show a level of connection as well. In this beautiful model that Clayton has suggested, the idea is basically the process of attention would start from those pieces that, if you remember, we discussed about before in this figure right here. Do you remember that? I discussed about this specific activation here in the cortex. This is right here. We call that, let's say, posterior middle frontal cortex, whatever we are going to name that, okay? Or something like the dorsomedial prefrontal cortex. Dorsomedial prefrontal cortex. So they start from here, and with theta frequency, this part activates dorsolateral prefrontal cortex, and then dorsolateral prefrontal cortex would get activated with gamma band. We know that gamma in DLPFC, it means that there is a kind of highly cognitive engagement here in prefrontal cortex. And this one would use the low frequency. By low frequency, we mean basically theta or alpha. So by low frequency, we mean something like theta would start from something like 3 hertz to alpha around 13 hertz. So this is the low frequency. So these pieces would start to work within the alpha or theta band, and they get engaged to each other. And then we have gamma here as well, which shows higher level of activation. So these pieces are highly active. Meanwhile, the system would shut down some other pieces that are not important. So if we are doing something like an externally oriented task, we do not need default mode network. So we turn down the default mode network, and we turn down the auditory cortex because we are highly attending to some specific visual field information that is not going to be really contributing to the auditory cortex. So we can turn off the auditory cortex. So technically what we do, we use this part to monitor and evaluate information, and then excite some pieces that are important and inhibit or turn down pieces that are not important in the brain. And how this system is working using different, let's say, levels of oscillation, different oscillator rates to manage this complex system, okay? But when we get to this level, the next question would be, okay, if this is working, is there any chance that I can use what we call external oscillation, and oscillating these areas from outside of the brain, through the skull, and trying to, using different oscillatory waves, let's say theta or alpha, or the ways that we are discussing, and get these areas connected. So we call it external synchronization, okay? And the idea is kind of using these, let's say, electrodes to be able to bring these networks on, something like modulating these areas. So without even having this part engaged, just activating these networks. Or even this part is engaged, we are just going to kind of boost up these activations. And we need to kind of have evidence that these parts are affected by different, let's say, kind of disorders. For example, in substance users, we have done a study. I don't have enough time to give you details about that, but we explored how these connection between frontal and parietal parts with different oscillatory rates would be affected in substance users. And here we have been using those who are using meth or crystal, opioids, and those who are using both meth and opioids. So these two together. And we explored the connectivity with beta band, alpha band, theta band, delta band, and also with Bolt signal. And you know the Bolt signal would be, the fluctuation in Bolt signal would be in the order of seconds, because in the Bolt signal we are not able to record the higher oscillatory rates, because what we had, the sampling rate frequency for us is something like 0.5 hertz. Because it is the half a hertz when we are doing the oscillation, we can just record things like at the kind of the oscillatory rate of something like 0.25 hertz. So we cannot sample things that are in the kind of the higher frequency oscillation. We can just sample the things that are in the upper frequency band because of the sampling rate that we have for fMRI. But we technically did an fMRI and EEG together to find connections that are significantly impaired by using these drugs, to say, okay, if we do the theta oscillation, we can help those drug users because these connections are impaired. So that's I'm not going to go to the depths of that, but that is the type of projects that we are doing in terms of, okay, is there any chance that we can engage these parts of the brain? Okay, that is the end of this part.